hears? Yeah. It's not a big hall, so. So I want to thank the organizers. I want to thank Sarah, my collaborator, and also Eric Lutz for the slide changer. And let's start.
This microphone is used to record. Okay, you have.
Yeah.
Okay,
yeah.
Good.
Okay. So before I start my talk, let me just, Ian Walmsley from Oxford was supposed to come here and talk about this experiment, but since he's not here, we uploaded this just about a week ago. It's an experimental validation of the equivalence between different engine types, the two-stroke and the continuous machine, and just write down the numbers, the archive number. And I'm actually a bit haunted by this paper, the theory paper that we did, because I get emails like this, that basically they tell me they read my paper, okay, which we greatly appreciate, and this actually I got yesterday. And then they invite me to a neurological disorder summit. So it's because it's a brain stroke, and I worked on two-stroke and four-stroke machines. And I think what I should do is actually go there and deliver a talk.
Maybe they just thought you were crazy, no?
Yeah.
Ticket classification is not to pay.
Okay, so
four-stroke is a record.
Well, maybe continuous is also not. Okay, so let's start. The typical setup I'm interested in is a case where we have a small system, just a few spins, maybe cutrates, and also our bath is also small, like Jörg was speaking about, but could be even very small, just 4 spins. And the only condition that we impose on this bath, or microbath, is that initially it's in a thermal state. After that, it doesn't have to be in a thermal state. Can be very far from equilibrium. And the interaction between them is described by some global unitary. And what we're interested is to make some thermodynamic constraints on observables in this system. That is, we want to make predictions without explicitly solving the equation of motion. Now, if we look on some of the available framework, with coupling, stochastic thermodynamic, and so on, so they have a hard time with this setup for various reasons, which I'm not going to talk about. However, if we look on the oldest trick in the book, the Clausius inequality, it works perfectly fine in this setup. The problem is that, first, it assumes that initially the system and the bath are uncorrelated. So this is one limitation. And in addition, it gives only one prediction that we already know what it is, and what we want to get is more prediction. So I'm looking for a framework that will be highly suited for this kind of scenarios. So let me start by presenting the Clausius inequality from a quantum thermodynamic perspective, and I'll also introduce a notation that will be important for later on. So we have several of these microbaths. We have a system, and the whole protocol of connecting the system to the bath and so on, the whole accumulated effect of this protocol is described by some global unitary. And therefore, the total density metric is related to the initial one by this transformation. Then we make the standard thermodynamic assumption on the initial condition of the whole setup. First, it is assumed, also classically, it's not always stated, but it's assumed that the system and the bath are uncorrelated, and that the baths are initially in a thermal state. And with this assumption alone, and together with this unitary evolution, one can get the Clausius inequality. There are at least 3 different derivations of getting it. What we have here is the change in the von Neumann entropy of the system. This is the change in the average energy of the cold bath, change in average energy of the hot bath. Slightly different from this textbook form, because this refers to changes in the energy of the system. And this is why we have a plus sign here. And this is perfectly valid even if the system is very small and the baths are also very small. It's also valid for strong coupling because it's valid for any unitary, and of course for non-Markovian dynamics as well. However, it's easily violated if there's initial system-bath correlation. There's another way of writing it. If we define this operator, which is minus log the initial density matrix of the bath, then you can see that these terms, because they are initially prepared in a Gibbs state, then these terms can be replaced by the change in this expectation value, which is an operator operates only on the bath. And this framework that I'm going to present is based on the idea of passivity, and Robert already talked about it, and Gershon as well. But let me repeat it for clarity. Given any operator B, the passive distribution with respect to this operator has the following form. If we sort the eigenvalues of B in increasing order, then the probability has to go down as we go up in eigenvalues. So the lowest eigenvalue get the largest probability, and so on. And if we prepare a system in this passive state, and we look on the expectation value of this operator, then we'll see that this expectation value must grow in time with respect to the initial value if we apply any unitary or even a mixture of unitaries. And this mixture of unitary will be important later on. So passivity was used in thermodynamics, well, in these papers, but it was more or less in the same context. Given the Hamiltonian of the system, what is the passive state of, with respect to the Hamiltonian? Because this tells us how much work we can extract from the system. However, if we invert the question, we can get many other results. And now we ask, given any state, what are the passive operators that goes along with it? Okay, so it's exactly the opposite question, and it's lead to quite a few results. And I'm going to, usually I don't make provocative statements, but I'm going to show, or to claim, or to pose the question, is passivity even more fundamental than the second law itself? Okay, so, in addition, passivity also gives practical tools for understanding and exploring concrete systems, and I'll show an example for that as well. So let's start. The setup I'm interested in is slightly more general than before. We may have correlations between the system and the baths, or between the two baths. And in addition, instead of considering just one unitary, we're considering a mixture of unitaries. And this describes the situation that we may have some noise in our control, and we think we implement unitary U1, but with some probability we implement U2. Okay, so that describes the fact that we may not have perfect fidelity in our protocol. We don't have to include this, but it's very easy to include it in the formalism. So the first claim I'm going to make is that if we define this operator, which is minus log of the total density matrix, including all the baths in the system and everything in our setup, then this operator is thermodynamically passive. That is, if we look on the expectation value of this operator, it will grow for any thermodynamic protocol. That is, for any selection of UK and PK. Now, some of you may see the relation to the second law, but I actually want to point out an important difference that one can see already at this point, that there's no assumption that the elements have to be initially uncorrelated. So this will grow even if you have correlation between the different elements. Now, to see the relation to the Clausius inequality, we need something a bit stronger than the passivity principle, some extension of it, and this is called strong passivity. And we start with this identity, okay, and there's nothing much to say about it. This is the change in the, we just plug in the definitions. Here we have the von Neumann entropy of the total setup, and this is the relative entropy, quantum relative entropy of the final state with respect to the initial. Okay, you plug the definitions, you get it. Now let's focus on this term. Yeah.
Any assumptions on the state? Not coming back full rank or so, otherwise the matrix not well.
So there is, for the bath, there's no problem if they are initially thermal and so on. And for the system, it comes out, it's true that this may be singular if you use this operator, or you can use other operators that don't have this problem, and you can still use the idea of passivity. So there is a way around it. But when you go to the Clausius inequality, you'll see that we don't have the total operator, and you'll see that we don't have this problem anymore. So somehow it works out, okay?
But sorry, you probably stated this already. Are you assuming that the baths are in equilibrium initially, or no?
So for now, no. Okay.
Okay, that's fine.
But I'm just saying it's not natural to assume that they don't have full rank.
Okay.
Okay, so if we have a deterministic protocol, a concrete unitary, then of course the von Neumann entropy of the total setup doesn't change. If we have a mixture of unitary, then you can show that this is never negative. Okay? It's not a statement of the second law. It comes from the fact that the von Neumann entropy happens to be a Schur concave function, and there are many other information measures that have this property. So this is not related to the second law. It just comes from this randomness that we have in the protocol. Again, we can, if you want, we can completely ignore this line and continue without this extension. However, since this term is never negative, we can just throw it away and get this inequality, which we call strong passivity, because this is, of course, never negative, so this implies the regular passivity that I showed earlier. So this is basically, if you want, this is a proof of claim number 1. But
Passivity of what? Of dynamics or state? Or
so passivity is always a property of a state and an operator. Okay? But now, instead of just telling you it must grow, I tell you that it must grow by this amount at least. Okay, so it's not just growing, it gives you additional information. Okay. And now we can use the information that we have here. We can use some analytical properties like joint convexity, and we can get extended Clausius inequality. Once again, we have the change in the von Neumann entropy of the system. This operator we've seen before, and we have a new one, which is a B system. It's minus log the initial state, the initial reduced state of the system. And if we compare this to the standard Clausius inequality, we see that basically what happened is that we replaced the bath operator by total minus system. Okay, so this is one take-home message, that if you have initial correlation, then instead of looking at the bath operator, you need total minus system. And there's another way of writing it. We can write the extended Clausius inequality as the standard terms, like in the Clausius inequality. But then we have this, this operator, which comes from the initial correlation. So it's total minus system minus bath. And in this form, it's straightforward to see that if we make the assumption that initially the system and bath are uncorrelated, then this operator is identically 0, and we get the standard Clausius inequality. Okay, but now let's see what we can do with this extended Clausius inequality. And this is actually the scenario that Jaynes was talking about, that initially the system and the bath together are in the thermal state, but not individual parties. So, and we may have additional bath here. So the initial state is described by this expression. And if we check what we get from the extended Clausius inequality, then we get this standard terms. And we have another term which comes from the interaction energy. So it's the change in the interaction energy. And there's another term that comes that basically describes the dressing of the bath on the system. So what we have here is actually the potential of mean force, which keeps popping out in the context of strong coupling. but we subtract from it the bare Hamiltonian of the system. So this is just a dressing effect. And in many cases, this is actually second order in the interaction energy, while this is first order. So this is usually stronger than this one, but not always. There are exceptions. Okay, so far we have used passivity to extend the Clausius inequality to the case of initial correlation, but there are other ways of exploiting passivity. So next I want to show that you can find systematic setup-specific bounds. So let's look at the following example. We have the standard Jaynes Cummings scenario, an oscillator coupled to a spin that can describe an atom in an optical cavity. And the question I'm interested in is what can we say on the buildup of correlation between the atom and the oscillator from a thermodynamic point of view. If we start without correlation, we know that it will build up, but can we say how big it must be or how big it can be? So this is what I'm interested in. And using passivity, we can get this type of bound on the energy covariance between the oscillator and the system. Now, this is different from looking on the mutual information or something like this. This is a measure of correlation which is measurable, okay, in contrast to mutual information that you actually have to do tomography. So this is something important in this passivity framework, that it aims to give prediction on observables. And the bound that you can get looks like this. There is a constant that you calculate before just using the initial state of the setup, very easy to calculate. And this is the total energy. And the only input that you need to measure is the average energy of the spin. So you measure only something very small, and you learn about the correlation between the oscillator and the spin. And this is how it looks like in practice. In blue, it's the actual covariance. And this is a lower bound and upper bound obtained from passivity. And as you can see, in some points, it is quite tight. Okay? And I remind that this is not from a thermodynamic point of view, this is not a reversible process. This is not close to thermal equilibrium where we expect things to be tight. And if we naively apply passivity, we don't get results which are that good. But the reason why the bounds are tight here is because I use this notion of constrained passivity. Basically, the idea is to incorporate some properties of the equation of motion into the idea of passivity. For example, if you have energy conservation or selection rules, then instead of looking at the passive states, you look on the most passive state given this constraint. Okay? And it turns out, at least numerically, it's just as easy as calculating passivity. Okay? It's a very simple thing to do. And just to show you that I didn't carefully choose some very specific example where it works, if I try to look for better parameters, then I can get much better, the bounds can be much tighter.
Sorry, Ram, just before you go on, I'm up here.
Oh.
So what I don't understand at this point is that, I mean, you mentioned that it's like measuring correlations, but there's this, of course, these results which were derived by Massimiliano and the mutual information when you do this type of a scenario. I mean, is there a precise relationship with what you're saying and the mutual information between the system and the
Well, the mutual information, it's actually the term that appear in the second law. When we say it's larger than zero, then this is one of the terms, right? Mm-hmm. But
like, where does it come in this equation? I mean, does it have any precise relationship there?
well, it doesn't come. This is not exactly what I use here. It's not exactly the second law. It's really the principle of passivity, that I have an observable and I ask what is the lower expectation value that I can put to this observable. And the point is that this quantity, unlike mutual information, you can build from observables. Okay, while mutual information you cannot. Perhaps a slightly more interesting scenario to look at would be something like this, where we have many atoms passing through the same optical cavity, and they become correlated because they interact with the same cavity. So this, similar to the experiments that Serge Haroche was doing, and perhaps even similar conceptually to to these units that Massimiliano is working with. And I'm interested in to make a prediction on the correlation that build up between the different atoms and also between the atoms and the photons in the cavity. So I haven't done this yet, but this is an interesting scenario. And finally, I want to show that one can get new thermodynamic inequalities, or if you wish, laws. So it's once you have this passivity mindset, it's very easy to generate new inequalities on new observables, because if this operator is, and it is, thermodynamic passive, then any positive power of it will also be thermodynamic passive. It takes about 50 seconds to show this, but I don't have this time, but it's really a simple argument. And if it's thermodynamically passive, it means immediately that the expectation value of this operator has to grow in time. Okay, so with zero effort, we can get these new inequalities, which are expressed in terms of observables. So here's an example of what we can do with them. We can detect Sub-Maxwellian demons. So let's consider the following examples. We have two cold spins and two hot spins. We apply some unitary, we let them interact. And then at the end, we apply some, with some probability C, we apply this feedback. If the demon measure that all spins are up, it changes them to down. Okay? And one way to check to see if a demon actually acted or not, okay, so the goal of the experiment will be to detect this demon. Then if we look on the increase of entropy in the cold bath and the hot bath, then we see that for this strength of feedback, it's always positive. So we cannot use the second law to detect this demon. Okay? It's too weak to be detected by the second law. It doesn't violate the second law. However, we know that if there's no feedback, then these laws should hold. Okay? But if there is feedback, they may fail. Okay. And so this is what we do, what is plotted here. We just plot what is the change in this expectation value, and different colors correspond, or different lines correspond to different values of alpha. And you can see that if alpha is equal 1, this is the blue line, that corresponds to the standard second law, then it's always positive. However, when we go to higher orders, then it becomes negative. Okay? And when we go to higher alphas, then we can basically detect weaker feedback. And there are interesting questions like how many inequalities we need. Do we need infinite, or do we need only, because it's a small system, do we need only a finite number, and so on. But I don't have time to talk about this. And the last result I want to show is related to the fact that this whole framework is actually sits on a deeper mathematical framework that is based on the Bregman divergence. And I'm not going to talk about this, but I just want to select one result that comes out from it. And that's the thermodynamic cost of creating coherence. So when we talk about coherence, first we need a coherence quantifier. And one of the ways of doing it is through information measures. So if you have a concave function g, you can always define an information measure in the following way. And once you have this information measure, you can define a coherence measure by looking at the information on the diagonal minus the information of the total density matrix. And you can show that this is always positive, and it's a plausible coherence measure if you look at this really seminal paper by Plenio. Now, using properties of this Bregman divergence and so on, again, I'm not showing it here, then one can get the following result. If we know that we have a certain amount of coherence in the final state, okay, for example, it's 3, according to some coherence quantifier, then this tells you that if you look on this observable, okay, g prime is just the derivative of g, it has to change by this much. So in other words, there's a cost, there's always a minimal cost of changing observables if you create coherence. So it makes sense, but this really quantifies this, I think, in a simple way. This is just an example. Maybe I will not go through the whole thing. I just want to show that if you make this choice, the simple choice that capital G is just minus x squared, then what you have on the right-hand side, the coherence quantifier, is just the sum of the off-diagonal elements squared. And what you have on the left-hand side, the observable, is something that looks like the exponent of the entropy production. Okay. Let me skip this in order to reach the final slide. It's more or less a graphical summary that shows that everything from this talk comes out from this principle of generalized strong passivity. From this you can get the extended Clausius inequality, you can get this Demon detection, you can get the thermodynamic cost of coherence and other stuff that I didn't talk about. Related notion is constraint passivity, which you can add to this, and then you can get this tight bounds, and also you can use it to study problems of energy storage and energy transfer. This is something I did with more people now, but it's still work in progress.
The heat that you had in the expression with the interacting thing at the beginning, you defined it in the traditional way with the energy going into the bath?
The heat?
Go back.
The change in the energy.
One slide, just a second.
Yeah, here.
Yeah.
So Q, how did you, it's the,
So Q is the change in the average energy of the bath.
That's there.
Yeah. And I don't,
Okay.
for this, the Clausius inequality doesn't care if there's some ergotropy inside and so on. It just gives
No, I simply wanted to make sure that this was
Yeah.
the definition.
Yeah.
Okay. So there's two notions of coherence measures or coherence operations. There's the one that you mentioned where, in some sense, you're allowed, you just need to preserve coherence, so you're allowed to, for example, swap energy levels, because swapping energy levels doesn't change the coherence properties of the state. And then there's another one, if you have a super-selection rule, then there's a different notion of coherence, because the super-selection rule enforces that. And you seem to show that this other one, the first one, was kind of relevant for thermodynamics, and that is a bit surprising to me, since
Well, because I think what you have
the
in
second
mind,
notion,
right? I think what you have
expect to
in
be relevant
mind,
and not the first
yeah,
one.
yeah. I think what you have in mind is that the coherence basically between energy level, different energy levels. Okay, and this you can show if you have energy conservation. You can show that if you start without initial coherence, you cannot generate coherence. But there are other types of coherence which are basically they are essential to energy transport. This is any coherence between degenerate space. For example, if you have two spins and you want to swap them, then basically you generate coherence between them until you complete the full swap. You actually have coherence between the two particles. So this is the kind of coherence that enters there, and it's always there, even if you have energy conservation.
In some of our work, we had one upper level and two lower levels, and then we send in microwaves and generate coherence, and then we get some improvement beyond some limit. But we always go back and calculate how much did it cost to generate that coherence. It's a quantum optical calculation. Can you get estimates on those kinds of numbers? How much did it cost from this approach?
So I think this is one of the cases that I want to check. One is what happens if you have squeeze bath and then you apply passivity without just see what comes out. And the other one is when you have this initial coherence in the degenerate space, like in your work, and I don't know what exactly would come out.
Well,
Okay,
we
but
published that in an obscure place, so I'll send it to you maybe.
okay.
Okay, so really the last question.
Okay. Again, the further forward, the interacting.
The interacting. You mean the one with the?
The two bath. and one
Yeah,
was
one which is, okay.
yes, there. Yeah, this expression. So if you simply take away the cold bath and you take the entire thing that is always greater than 0, have you tried to compare this with what you would get from the Jarzynski W minus delta F, where the delta F is the interacting F, where again the potential of mean force shows up?
Well, it's, I think fluctuation of work is slightly different language.
Yeah, but take
than-
expectation value, which you know that the work minus the change in...
so you're saying to look at fluctuation of work in this case,
Yes,
and see what comes up.
Yeah, I wonder how it is related to this quantity that you have.
Right, or maybe one has to do this form with actually with entropy assigned to each trajectory and so on, because we want to compare it to
Even
something
expectation value would be fine. I don't really care about fluctuation, but I know that the work minus the change in free energy has to be always positive, but that free energy is the one that you get from the...
Okay, so I have to look it up actually. There is something here. This term is actually works on coherences because it's something that connects, let's say, your two spins. This interaction, let's say, it's just two spins.
Yes, the initial.
Okay, and this actually works on coherences. The leading order is when this what creates current. So I'm not sure how it will appear when, but I want to try it. Yeah.
Okay, thank you again.